For this last lesson on thermal effects of nuclear weapons, we're going to look at what happens when that thermal radiation is incident upon different types of materials that make up structures, clothing, newspaper, trees, and people. Okay, so to start off, what makes the thermal radiation from a nuclear weapon so bad? Well, thermal radiation is coming down all the time from the sun, right? We have a relatively low level of thermal radiation depending on atmospheric conditions. That's always incident upon just about everything. Now the difference is in the amount of radiation that is introduced, the amount of energy deposited over a certain period of time. Now the best example I can give is imagine that you have a piece of steel. And you have this piece of steel just sitting under the hot sun. It's a summer day. There's no clouds. It's a clear sky conditions. There's no real wind for additional cooling effect. You leave that plate out there for 12 hours. By the time you come back and touch it, it's going to be quite hot. That said, even though there's no wind and it's just sitting there and looks like it's doing nothing, it's absorbing that radiation, that heat, but at the same time, it's also getting rid of it, just to the atmosphere through convection. So it's getting heat put into it, but during that same amount of time, it's losing heat, so that the total amount of energy buildup in this plate of steel is less than if you just, summed up how many, how many calories per square centimeter over that entire 12-hour period would you think you ended up with? Now, alternatively, you could take that same piece of steel, prop it up on, like a pedestal of some sort, so that you have access to more of the surface area, but still only getting that radiant energy on the top side. And you could aim a fan at the bottom of it. Now, the fan with the moving air is going to be able to remove even more heat than it just sitting there with no air circulation over that same period of time, so that at the end of the day, the steel is going to be relatively cooler than it was without that airflow removing some excess heat. So it's all about heat deposition over time. So let's look at the example I've got right here. Imagine that you have a heat source. Call it a food heat lamp. And this heat lamp is putting out 1.5 calories per square centimeter per minute. And we're going to run it for 10 hours. Okay, now underneath it, we're going to put, a block of wood. Okay, that block of wood can sit under the heat lamp with that kind of radiant exposure for 10 hours, and basically nothing's going to happen to it. All right, it may turn color slightly, but nothing's really going to happen to it. You take that same block of wood, okay, so you have a total radiant exposure of about 900 calories. Now, take that same block of wood, expose it to 300 calories per centimeter square per second for 3 seconds, and it's going to burst into flame. Same amount of heat, but concentrated in a much shorter period of time. So the block of wood has no ability to reflect or re-radiate or get rid of that heat or mitigate the incident radiant exposure, in that 3 seconds that it did over that entire 10 hours. So it's all about the delta E, or the energy being deposited, or the change in energy in the material over some amount of time. Again, it's not just deposited, because it's also some materials can get rid of this heat. Now you have 3 options when it comes to mitigating incident thermal radiation. So the first one you have right here is reflection. That is when you have your thermal radiation coming in, which is the black arrows, but the surface or the material is prepared in such a way that that thermal radiation reflects right off of it. Think of something very highly polished, or for optical photons. And then I guess there's a way you could probably do it with infrared and lower frequency photons. But the whole idea is that your material has the ability to reflect this incident thermal radiation from itself. So it's not going to get nearly as much energy deposition if it couldn't do that. The second one, which is down here, is transmission. And this could be something like a piece of metal that's in contact with something else, another piece of metal per se. And this is how heat sinks work, right? So you have something really hot, and then you have a big block of something right next to it, which basically just draws out the heat as fast as it's being deposited, usually in electronics. So in this case, the heat is going in, but then it's being pulled right back out due to transmission through a highly thermally conductive material. And then the last option is the kind of one that happens most times, which is absorption, which is that radiant energy hits it and it just keeps depositing, and it just increases the temperature of the surface or object or material that it's incident on. So you can reflect some of it away, you can transmit some through it if it's got a high thermal conductivity, or alternatively, you just keep dumping energy into it. Now, absorption, the effects of absorption, because of the types of large thermal fluxes that we're dealing with here, the internal energy of the material can increase extremely rapidly if there's no way to remove that energy that's being put into it. So as that energy increases, then the overall temperature of the material increases until the point where we can start seeing some physical changes. Now, in Hiroshima, they tried to figure out, or they did figure out, what the temperatures were at certain locations from where the weapon, like the ground zero where the weapon was detonated. And they did this by looking at certain things, like looking at telephone poles that were charred, looking at some surface abrasion of granite, looking at deformment of these green ceramic tiles. And the way that they were able to figure out what temperature was specific to a given region, given these indicators, is they kind of just took stuff in the lab and burned it, or exposed it to a high enough radiant energy flux so that it produced very similar conditions. So after they did this, what they found out is at ground zero, directly under where the weapon detonated, there were temperatures between 3,000 and 4,000 degrees Celsius. And even at a half a mile away, the temperatures were still at 1,800 degrees Celsius. So just the amount of heat, the amount of energy being deposited by that radiant thermal flux is just enormous, even at a half mile away from ground zero. And of course, this energy deposition occurred over an incredibly short amount of time, not allowing the material to shed some of that incident radiative energy and not undergo some of these transformative changes that they underwent. So we have some pictures here about certain effects that are materials. The house pictures, the two pictures on the left-hand side are very famous. These are from a test done out at the Nevada test site. I think this footage was featured in like one of the Terminator movies or something. Anyway, what it shows is the thermal effects on a wood frame house 1 second after detonation with a radiant thermal flux of approximately 25 calories per square centimeter. And what you see is after 1 second, that thermal radiation hits the house, and immediately the wood on the outside of the house just sort of chars and releases all this smoke. It's just like an instantaneous oxidation reaction with the wood. So if you look at it about 3/4 of a second later, it's the house isn't even on fire, but you see what happened when that thermal pulse, if you will, struck the surface and badly discolored and charred the wood face of that house. Now over on the right hand side we have pictures from Hiroshima. So these chairs that you see, basically there was a window that looked into a room, and that the light coming in through the window partially illuminated these chairs. Well, that was the avenue into which this thermal radiation could impart energy on these chairs, but only in the spots where the light was shining through the window. So you can see the rest of the chairs are fine, but right where that window openings were, right where those window openings were, we see some serious discoloration of the material of the chairs. Now it's black and white. It's kind of hard to see exactly what happened, whether or not that's black and the chair's material was some brownish type of color. It's hard to tell exactly how much discoloration occurred or to what extent, but again, the point is that there was an aperture, a window, where photons could stream through, and of course they did, and they damaged whatever they hit, and nothing else was touched. And then we have it looks like a shadow on the wall of this valve, this pipe valve, except it's not a shadow. It's literally like the only place where the paint wasn't damaged was where that valve stopped those photons from hitting that surface. So everywhere else, they imparted a ton of energy into the surface, but right where the shadow was being cast by the valve, where the photons were not allowed to hit, it fared much, much better. And this is 1.3 miles from ground zero at Hiroshima. And then finally, a very famous picture all the way on the right-hand side of a Japanese woman showing the burns that occurred on her body from the photons being able to penetrate through her clothes at certain points, which is why she has these patterned burn marks. Would have matched up to whatever shirt or blouse that she was wearing, and places where either she wasn't facing the detonation or was covered by a much thicker material that didn't allow the photons to penetrate and pass on that amount of energy, is not burned. Okay, these tables are in ENW, and it's just how much radiant exposure do you need to light stuff on fire or to do some other effects on the materials. Now, on the left-hand side, it's basically just stuff lights on fire. And it goes through paper and cotton, wood, roofing materials, and then I just sort of cut it off. And then the table on the right-hand side looks at radiant exposures to make certain kinds of fabrics ignite. And in this case, we have cotton, different types of cotton, wool, some rainwear, which is some nylon. But what I want you to notice, first of all, in both of these, as we saw before, the radiant exposure required goes up with yield. Again, that's because the amount of time that it takes for a 35 kiloton blast versus a 20 megaton blast for all that thermal energy to be transmitted. Now, if you look at the fabrics for cotton, different colors have different radiant exposure ignition temperatures. So white for 35 megatons, I'm just going to use 35 for this because it's the first one, it's easier. White ignites at 32 calories per square centimeter. Khaki ignites at 20, and then a much darker olive at 14, and then dark blue at 11, brown also at 11. So what we see is not only is the material important, but in this case the color is important. And why is the color important? Well, it's that reflective capability. Remember the three ways of being able to get rid of some of that heat or avoid absorbing that heat. Reflection is a very good one. It's one of the best ways to avoid having thermal radiation deposit its energy if you just reflect it back the way it came. So the lighter the color is, in this particular case for optical and even for some lower energy photons, that white is going to not want to absorb most of the light that's hitting it. It's going to want to reflect it. In fact, that's kind of the definition of white, is it reflects most wavelengths. Now, if you get into something like black, definition of black is it absorbs most wavelengths, and then everything else falls sort of in between there. So what you end up happening is the lighter color of the material, the more it's going to reflect that thermal radiation, and the darker the color, the more it's going to absorb that radiation. So it's going to take less of a thermal flux to ignite or damage a darker temperature than it is for a lighter color. So what does this mean? You know, in the grand scheme of things? Well, it means that we can take a look at those tables, find out, you know, what kind of radiative exposure that we need in order to damage that material. And then we can come over here to this cool little table and find out, well, okay, given a certain yield of our weapon, how far away do I have to be to not have that thing happen, to not have it ignite? So an example would be looking at a 1 megaton burst, okay, and then we're going to see what kind of range, and this is the slant range in miles, how far away do I have to be before paper doesn't ignite? Or put alternatively, how close do I have to be until paper ignites? Okay, so for 1 megaton, we're going to be looking over here, that's 10 to the third kilotons. Okay, so this line is what we're going to be using. I'm going to just draw on here. So that line right there. Okay, now we're going to go look at newspaper. Okay, so we go for newspaper, dark picture area, printed text area. We'll call it printed text area. Okay, so it's going to ignite. Okay, 1.4 megatons. It's going to take about 8 calories per square centimeter. So 6 is at 35 kilotons. So we'll just go ahead and call it 9 for 1 megaton. So what we need to do is we need to say, okay, well, here I am on, this is my yield. Erase that. So this is my yield line. Eventually it'll write. There we go. Okay, so I need to be at 9 or below, 8 or below, in order for my newspaper to not catch fire. So we'll see that the 8 calories per square centimeter crosses the line right about here. I don't know why it does that. Okay, so then we just go ahead and look all the way over here to where does that hit our axis. It looks about, probably right about here. So that's about 7 miles. So at 7 miles and further, let's make sure that, yeah, okay, it was 8. Sorry, just checking. So at 8 miles, or sorry, 7 miles and further, our newspaper will not ignite because the amount of energy being put on it per square centimeter is just not enough. Anything closer than 7 miles, though, it's going to burst into flames. That's basically how you use those tables with this cool little graph in order to find out how far away do you need to be to avoid a certain effect. Now, with the information that we got from Hiroshima and Nagasaki, this is in ENW in Chapter 12, about 20 to 30% of all the fatalities were caused by basically flash burns. That is the same thing that happened to the house when it got hit with that thermal radiation and deposited energy very quickly. We saw the wood charring and immediately oxidizing. Same thing happened to people. except it was not wood. Obviously, it was their skin and all that energy being deposited. Basically, just was extremely fatal. Now, in Nagasaki, there were 42,000 burn cases reported, 24,000 of them which were considered serious. In the open air, unshielded exposure, that is just nothing between you and the radiation coming off the weapon, at about 1.1 miles would have been just fatal. Flash burn fatal. However, if you move past that, while not being fatal, is still considered serious all the way out to about 2.5 miles from that ground zero point. So again, it's just like those curves we saw in the previous graph, that as you move away, the amount of radiant exposure that you're being, that's incident on you goes down so that the effects are lessened. Now, interestingly enough, the eye injuries, there were people that were rendered flash blind, which is a temporary inconvenience. Your eyes do recover from that. And that would have been, they would have had to be looking, towards where the detonation occurred, when it occurred, in order to get a pretty large photon flux directly into their eyes that would cause this flash blindness. Now, the other thing that could have happened was extreme retinal damage from basically way too much energy entering into the eye. But surprisingly enough, not many people suffered from this. And one of the things that was used to explain is that blinking during this radiant exposure period would have seriously offset the amount of energy being put into the eye. You could get enough to cause flash blindness, but not nearly enough to cause any severe, long-lasting retinal damage. Because, obviously the skin of your eyelids are going to stop those photons from hitting your eye. Okay, a couple last charts. These are pretty straightforward, and they work the same as what we've seen before for burn injuries. So there are 3 different types of burn injuries on the left-hand chart: first degree, second degree, third degree, and they're grouped by skin tone. So light skin color, medium skin color, and dark skin color. And this works exactly the same way as what we saw with the clothing materials. Lighter reflects more light, darker absorbs more, so that you have a higher energy deposition. So again, this is how we would use the chart. We will find our explosion yield. So let's, again, we'll go with a megaton. So that's this line right here. Okay, and say that we calculate for a specific distance that these people would be, that the radiant exposure was going to be, we'll go with 6.5 calories per square centimeter. So if we look at 6.5 and we cross over, we're going to be right about here. Which means that we're going to get second degree burns and basically all skin tones, light, medium, and dark. Now, if the radiant exposure had been, say, down here somewhere, as soon as I find my thing, if it was here, that would have corresponded to about 5 calories per square centimeter. So you would get second degree burns had you had dark skin, but a light skinned person would have gotten away with just first degree burns. And that's basically how you use this chart. You have your explosive yield in kilotons, and you can either use one of the other figures where we looked up what the radiant exposure was as terms of slant range and weapon yield, or you could use that Q equation that we could figure out what was the radiant exposure given the thermal partition factor, the yield of the weapon, the tau, which is the shit. So you could find the radiant exposure by either using the figure that we did before or using that Q equation where we needed to know the slant distance, the thermal partition, the transmittance, tau, and the weapon yield. So we could plug all the numbers in, we could calculate it, and then we could come to this chart. Or again, we could just sort of back of the envelope it off of that graph that we had. Now this figure over on the right hand side, so this is population, unshielded population, radiant exposures, 50% of the solid lines right here. This would cause second degree burns in 50% of unshielded population. This would be third degrees and obviously first degree burns as well. And so that's basically the 50 degree line. This is 0 and this is 100. So again, let's look at our 1 megaton, our radiant exposure at about 6.5, which is going to put us somewhere, I don't know, somewhere right about here. So what this is telling us is that we're approaching right where this line crosses. We're approaching almost 100% of the unshielded population will suffer second degree burns because it's at this dotted line and not the solid line. Okay, that's pretty much how you use this chart as well. So we're just looking at we're either going to get first degree, second degree, or third degree, and then what percentage of the unshielded population is going to get that. Whether it be 0% of them, 50%, or 100% of them. Now finally, we're looking at eye effects. And again, this is just like we saw before, which is finding our explosive yield. This is a little bit different because this does not rely upon radiant energy. This just relies upon visible photons that are generated as part of a weapon detonation, which are dependent only upon how far it is from you and what was the yield of the detonation. So if we look over here, oh, and the reason that there are two of these is because this one is at day and this one's at night. Okay, so if we look at the day one, and again we go to our 1 megaton, and we want to know, okay, for a height of burst of, well, let's look at one of the dotted lines for flash blindness. Okay, so this one is going to be the curve for 10,000 feet. So if we want to look and see sort of where that goes, we just trace that down somewhere, probably there, about 15 miles. And then if we look at the height of burst being 50,000 feet, then we would have to be more than, probably, yeah, more than, I don't know, 17 miles, maybe 18 miles. I really suck at drawing a straight line with this thing, but if you had a straight edge, you could just lay it down and then find exactly where it crossed. Okay, so you'd have to be greater than those distances. Same goes with the retinal burns. If you wanted to avoid a retinal burn at some distance away for a 1 megaton detonation, it crosses right there. So it's probably going to be somewhere right around here. And that would be for 10,000 feet. And then for 50,000 feet, it would be a little further over, so right here, which would correspond to probably somewhere around here. And the same applies for the nighttime figure. So it's basically just drawing lines from, what's your weapon yield, see where it crosses the line for whichever height of burst and effect that you're looking to avoid. And then wherever it crosses the axis, you have to be farther away from that in order for that effect to not occur. So that wraps it up for thermal effects. For the next lecture, we're going to be looking at air blast and shock, which is that second part of the energy being carried away from the nuclear weapon detonation itself.